Welcome everyone to page number 7 of the Fall Semester 2014 final exam for Math 234. This page we're going to express x minus 2 quantity squared plus y squared equals 4 in the terms of polar coordinates, solve for r, simplify as much as possible. Alright, so let's get to it. I need to remember that x is the same thing as r cosine theta minus 2. We're going to square that. We're going to add it to y squared. Remember, y is the same thing as r sine theta. Square that, and this is going to be equal to 4. And my goal is to try to solve for r. So let's go ahead and expand these things a little bit. So when I expand this, notice I have to FOIL this term, right, because it's a binomial. So I'm going to have r squared cosine squared theta minus 4r cosine theta plus 4 plus r squared sine squared theta is equal to 4. So again, this is me FOILing out this binomial, and then I can just distribute the squared to kind of the r and the sine here because this is with multiplication, and then 4 is just 4. Alright, so at this point we can see there's a little bit of cancellation going on. There's a 4 and a 4 here, so I could subtract 4 from both sides, and that would leave 0 on the other side. We can also notice that we have an r squared cosine squared, r squared sine squared. So if we were to factor out an r squared from those two terms, we would have cosine squared plus sine squared, which is of course 1. So that would leave us with r squared times 1. Let's see, we have the 4r cosine theta still. That doesn't really cancel with anything. And again, we have 0 on the other side here. So now let's go ahead and rearrange, and I'm going to get r squared is equal to 4r cosine theta. And assuming that r is not equal to 0, then we wouldn't have any problem with just canceling an r on both sides. So I'm going to get r is equal to 4 cosine theta. And that makes a lot of sense, right? Because we know, looking at this equation up here, that this is a circle, right? It's a circle that's been shifted over 2, not up or down at all, and it has a radius of 2. So r equals 0 is just a dot, right? So that's kind of an extraneous solution. This one right here will actually give us the equation for a circle. And we could verify that if we really wanted to by graphing it. Alright, so that's part A. Part B, do not evaluate, right? We want to express but do not evaluate a triple integral in cylindrical coordinates for the volume of the portion of the sphere contained in the cylinder. So really quick, let's go ahead and try to visualize this and see what on earth we're doing here. Right, so let's see. Again, I know that this is a nice cylinder. It's been shifted 2 in the x direction, so its center is around 2, 0, and it has a radius of 2. So I think it's going to look something like, well, let me kind of extend this a little bit. So there's 2, and that goes out to 4. So I think this cylinder is going to look something like this. And of course, it doesn't have any z coordinates, so z is kind of free to roam up and down, so maybe something like this. And it can roam down, that's fine as well. So we have this cylinder right here. Okay, and we would like to know the volume of the portion of the sphere contained within the cylinder. So this is a sphere of radius 4. So maybe if I was to go ahead and use purple here, we already have 1, 2, 3, 4 out in this direction. We can do 1, 2, 3, 4 in that direction. 1, 2, 3, 4. 1, 2, 3, 4. So here it is, maybe in the xy plane. And of course it goes up and down like so. So there's maybe our sphere. So this is pretty interesting, right? It would kind of intersect maybe the cylinder at kind of, an edge or something like this. So maybe it has some curvature to it. Something like so. And I would like to know what is the volume of the portion of the sphere that lies inside of this cylinder. So here's maybe the top half, the top part, here's maybe the bottom part, and of course there's all of this stuff in the middle inside of the cylinder. So okay, this is the volume that I'm trying to find here. So let's go ahead and set up our integral. We know in order to find volume, this is going to be the integral of 1 dv over our region. And we're going to set this up in cylindrical coordinates. Right? So when I switch this into cylindrical coordinates, then I'm going to get an r, dz, dr, d theta. And we kind of already know maybe when I smash this down into 2 dimensions, right? So this is now in 3 dimensions. If I smash this down just into the xy plane, we know that, again, kind of this cylinder right here has been shifted over 2. So here's where the center is, and so we get something like this. So if I was to maybe shade in this region in the xy plane, when we smash this down just into the xy plane, right, we would get something like this. Alright, so now I'm ready to start writing down our bounds. So we're first traveling in the z direction. So imagine I'm traveling in this nice z direction. I'm going to enter in through the bottom portion of the sphere. So if I was to go ahead and take this and solve z equals, I would get, let's see, z squared is equal to 16 minus x squared minus y squared. And then I'm going to take the square root, and I'm going to get square root of 16. And let's go ahead and write, I know that I'm going to do this in cylindrical, so let's change this x squared y squared into r squared. Now, because it's the bottom half, right, the negative z values, right, when you take the square root, technically there's a plus or a minus. So I'm going to choose the minus one in this case. So therefore, we're going to enter in through the negative square root of 16 minus r squared, right, that's our z value. And then we're going to exit through the top piece. Well, the top piece is going to be the positive square root of 16 minus r squared. All right, after we go in this z direction, right, we smash down into just the xy plane, and now I'm looking at something like this. And let's think about, okay, as I travel in the r direction, right, so r starts at the origin and radiates outwards. You can notice that as I take even the tiniest little step, we start into our region here. And we always seem to exit through this circle. So therefore, we should have that the lower limit of integration is 0, right? As soon as you take the tiniest step off the origin, you're immediately into that region. And then you exit through that circle. And that circle has, well, that's part A, right? So we have that circle is r equals 4 cosine theta. So we're going to exit through 4 cosine theta. And now finally we have to think about what are our theta values. So certainly theta equals 0 should be in there. And maybe theta equals pi over 6, and maybe like pi over 4, and maybe even like pi over 3. And then maybe like at pi over 2, right, we're like perfectly there at the start, right? Because if I was to plug in pi over 2, cosine of pi over 2 would be 0. So I think our upper limit of integration should be pi over 2. How about our lower limit of integration? Well, certainly maybe like negative pi over 6, and negative pi over 4, and negative pi over 3. And then if we're at negative pi over 2, right, cosine of negative pi over 2 is also going to be 0. Right? So I think our lower limit of integration should be negative pi over 2. If we go any farther than this, right, our r values are going to start being negative. And I don't really like negative radius values. All right, we go back and we read the question one last time, and it says set up, right, but do not evaluate, or express but do not evaluate. So here is the volume expressed as a triple integral in cylindrical coordinates, but we don't have to evaluate it. All right, one more problem on this page, problem number 17. Evaluate this integral in spherical coordinates. So it's being nice to us, right? It says in spherical coordinates. So let's go ahead and do that. So I'm going to go ahead and start switching this over. Z is the same thing as r cosine of phi. And then when I switch dz, dx, dy into spherical, right, I'm going to have this rho squared. This is, sorry, and I said r, I meant rho. Rho squared sine phi. And then I'm going to have d rho, d phi, d theta. So at this point, I need to start drawing some pictures in order to figure out what should my new bounds be. So I'm going to first of all just try to sketch the two-dimensional picture here. So I'm going to do the two-dimensional picture, and then I'm going to do the three-dimensional picture, because that one's maybe more difficult. So let's just do the two-dimensional picture, right? After I integrate z and z's are gone, I'm going to be in the xy plane. So here is the xy plane. And let's see, y ranges, right, because that's my last one right here, y ranges from 0 to negative 3. So we're going to have from 0 down to negative 3 down here. So that's where my picture is going to live, kind of in this region between 0 and negative 3. And let's see, we have that we enter into the region through x equals 0. So x equals 0 is a nice straight up and down line here. It's the y-axis. And then we exit the region through the square root of 9 minus y squared. So that is, again, x equals the square root of 9 minus y squared. If we go ahead and we solve for this, right, we get x squared plus y squared is equal to 9. So this is a circle of radius 3. So in this region, right, there's circle of radius 3 over here, and there's circle of radius 3 over here, right? And of course, kind of the circle of radius 3 would continue up here, but again, kind of our picture is between y equals 0 and y equals 3, so we really don't care about those bits. And so the question is, okay, well, which one of these do we need to keep, right? And so we have a positive square root here, which means that those x values should be positive, right? Because as you plug in different y values, that positive square root is going to give us a positive x value. Well, positive x values, right, so here's positive 1, here's positive 2, here's positive 3, right? Positive x values live over here on the right-hand side. This is where the negative x values live. So we're going to go ahead and erase that, and now we can clearly see that maybe for just our two-dimensional picture, this is where we're integrating over. And let me go ahead and include here, so this is x equals 3, y equals negative 3. Okay. So now let's try to figure out for the three-dimensional picture, right? So if I was to go ahead and graph this in 3 dimensions now, so here's x, here's y, here's z, and let's try to graph this bit just in the xy plane in our three-dimensional picture. So we need x is positive 3, so 1, 2, 3, so up here. Let's see, y is negative 3, so here's 1, 2, 3 in the negative direction. Over here, and so let's see, it's going to be the quarter of the circle that lives over here in this region right here. Okay, now let's figure out what the three-dimensional aspect is, right? So let's now look at this last bounds of integration. We enter into the region through z equals 0. So z equals 0 is how we enter. So as we move upward, right, we enter in through z equals 0, aka the xy plane. So that's very nice. I already have this sketched. And now we're going to exit through z equals 9 minus x squared minus y squared. So, I mean, already, because I'm doing it in spherical coordinates, I'm thinking this is probably a sphere, but let's double check, right? So I have z is equal to the square root of 9 minus x squared minus y squared. I square both sides. I get z squared is equal to 9 minus x squared minus y squared. And so rearranging, I get x squared plus y squared plus z squared is equal to 9. So this is indeed a sphere of radius 3, right? Because 3 would be r squared here. Okay. Or rho squared, even better yet. All right, so this, we exit through the sphere of radius 3, but just on this region, right? So I'm going to go ahead and maybe try to draw the sphere of radius 3, 1, 2, 3, and that's how we exit through it. Notice that this is the positive square root, so this is positive z values, right? So we're exiting through the positive part, right? The upper part of the sphere. So let's go ahead and maybe draw something like this. So this right here is the region that we're integrating over. Maybe I'll go ahead and shade the surface of the sphere purple, why not? And then, right, this would be maybe like a side or something like this. I'll shade this green for fun. All right. So there is our picture. So trying to figure out what are our row bounds of integration, right? Well, I'm going to start at rho equals 0, and as soon as I take a tiny step, I'm in this region, and I'm going to leave through rho equals 3. So 0 to 3. We can also get this from the equation right here, right? Rho squared is equal to 9, so therefore rho is equal to 3. So because we exit through the sphere, I use the sphere's equation, and I can solve this for rho. All right, next up, thinking about our phi values, right? So phi starts at the positive z-axis. So as soon as you kind of rotate off a little bit, right, you're immediately in this region. So I'm going to do phi equals 0. And we stop when the angle reaches kind of this 90 degree, right? After that, we're going to be kind of down and we're out of the region, right? Because this is only the top half. So this is going to be from 0 to pi over 2. And then finally, our theta values. And for our theta values, I really like to go back to the xy picture here. All right, so just in the two-dimensional region. So for theta, I would say, right, and there's multiple ways that we can go ahead and write this down, but I'm going to go ahead and say from negative pi over 2 until 0, right? So I enter in through negative pi over 2, and then you keep going, keep going, keep going, keep going, and then at theta equals 0, that's where you exit out of the region. So again, having the two-dimensional picture and the three-dimensional picture really comes in handy. Okay, so that's all my setup here. Notice it does say evaluate, so not just setup, but evaluate. I think this is going to be the most difficult part, though. The evaluation really should not be so bad. Okay, so looking at this, for instance, I see that I don't have any thetas. No thetas in my bounds, no thetas in the functions down here. So if I integrate with respect to theta, right, I'm going to get, well, the integral of 1 is going to be theta, and then I'm going to evaluate 0 minus a negative pi over 2. So when I integrate my theta, right, I just get 0 minus a negative pi over 2, so that's just pi over 2. Okay, so let's go ahead and maybe erase all that. All right, how about when I integrate with my phi, right? So when I integrate with phi, I'm going to have cosine phi, sine phi. Notice that this is a product of functions, right? So a product of a function that depends only on phi and a product of a function that, right, only depends on rho. So here's the stuff that maybe just depends on rho. So I'm going to kind of break these apart. This is what enables me to do that. And so when I integrate cosine phi, sine phi, I think I'm going to get something like sine squared phi. But I'm going to need a 1/2, right? Double check. If you take the derivative of this, right, you should get back to where we started, right? Sine phi, cosine phi. We're going to evaluate this from 0 to pi over 2. And then when I integrate rho, let's see, well, my rho function is 4, and then I'm going to have rho cubed. So when I integrate that, I think I'm going to get rho to the 4th. And I'm evaluating that from 0 to 3. So you can see that this triple integral is really nice actually in spherical coordinates because, right, all of these are constants, 0 to 3, 0 to pi over 2, negative pi over 2 to 0, and we have a product of just a theta function, 1, just a phi function, cosine phi, sine phi, and just a rho function. That's going to be 4 and then rho cubed in this case. So you can integrate those kind of independently, multiply the results together. It's very nice. So in this case, let's see, I'm going to have pi over 4. I'm going to group these together, right? And so, okay, sine squared of pi over 2. So that's going to be 1 squared, that's going to be 1. Minus, when you plug in 0, that's going to be 0. Let's see, you take 3 and you raise it to the 4th power. So that's going to be 3 times 3 times 3 times 3. I think we're going to have 81 altogether. And you subtract away when you raise 0 to the 4th power. So altogether, I think I get 81 pi over 4 as my final answer. So again, the evaluation was not so bad. The setup is the important part for this question. All right, that's it for this video. I'll see you guys next time.